Hello everyone, I'm James Bonner, an independent scientist from Racine, Wisconsin. So let me start off by saying that if you are a chemist, you are never going to forget the day you found this video. What I want to tell you about is my 30-year-long research project, which at least partially was about finding a way around the quantum many-body problem. I need to tell you some history. I started out my education as a biochemistry student. I learned some fascinating things, but it bothered me that despite all of the detailed knowledge of chemistry and biochemistry, we've been unable to actually cure any genetic disease. Why not? The course of the rest of my education was trying to understand that one question. Laymen often wonder, why is it so hard to cure cancer? So, if you're a chemist or physicist, you probably already know what I'm about to tell you. But I have a few things that I should say for the laymen that are watching this video. So, the scientific laws that govern the behavior of electrons are collectively known as quantum mechanics. It is the behavior of electrons in the outer shells of atoms that govern the behavior of atoms and molecules, and the course of chemical reactions and so forth. So these equations can be solved numerically on a computer, but only for very simple systems. I earned a degree in physics just trying to understand the situation. So, in short, the computational effort and memory it requires to accurately model chemical systems scales exponentially, like n to the 7th power, n being the number of electrons involved. After years of trying, I came to the conclusion, as does everybody else, that the situation is impossible. We simply cannot simulate molecular systems that are chemically interesting using quantum mechanics. So, is nature trying to tell us something? Let's consider some things. For example, when an astrophysicist calculates the orbit of the moon around the Earth, does he take into account the quantum mechanical orbits of every subatomic particle making up the moon? Of course not, even though quantum mechanics is just as true at the macroscopic level as it is at the microscopic level. Yet new, simpler laws, which we call classical laws, emerge. These are actually approximate laws and are an example of what are known as epiphenomena. Since this happens for astrophysicists, might it also happen for chemists? Are there epiphenomenon that govern chemistry? Epiphenomena not related to scale, but rather to the attainment of stable molecular states. If these epiphenomena exist, how do we find them? If we can find these epiphenomena, perhaps we can avoid using quantum mechanics completely, at least not in an explicit way. So the good news is that I've found a way to do just that automatically. So the difference between today and years past is now we have data, and lots of it. By the way, if you would like to download a chemical reaction database for free, visit the link on my YouTube channel. Also, while there, watch the video titled Artificial Intelligence, Gene Therapy, and Cancer. It has a link to the paper and files and database, etc. Since we have the data, we can use AI to learn to pattern match reactants with their product. When I first discovered the technique to get around the quantum many-body problem, I was absolutely blown away by how accurate it could match these pairs. It almost feels like magic. Now I have a tool that I can simply point at a problem and get a meaningful answer. I'm leaving all the details out of this video. If you want the details, visit my channel, watch the videos, and click the archive.org link where you'll find the paper and files and so on. Also, please subscribe to the channel and thumbs up the videos. If you do, you're helping to promote awareness of the technology, because my videos will get more impressions. Now, I'll close by telling you that I'm using the AI technique I invented, which I've taken the liberty to coin Bonner's algorithm, to study chemical reactions involving DNA. Imagine being able to do that. You can too. It feels almost superhuman. It kind of reminds me of the first time I saw any of the magical mathematics that Ramanujan invented, except here we're doing the same thing for chemistry. The best thing about Bonner's algorithm is that it is fun to use. If you can't have fun as a scientist, it ain't worth being a scientist. Now, I should say you will have to have a well-rounded scientific education to understand the paper in its entirety. But I wrote the paper in a textbook fashion, so I'd have as many people understand it as I possibly could have. That said, I hope you have fun learning about my research and tinkering with the computer programs. Maybe you have something to add to it. Who knows? Anyways, a new day is about to arrive in the chemical and life sciences. I'm going to have the time of my life watching it happen. Till next time, goodbye.